So this is the big multi-step Q problem where we're looking at how much energy it takes to do all the way along this heating curve. How much energy it takes to go from ice at a cold temperature, heat that ice, melt the ice, heat the water, boil the water, and then heat the steam. So there's 5 steps to this, and it's simpler than it looks because we're doing each 5 of those steps separately. So let's take a look at what the problem says first. It says, how much energy does it take to raise the temperature of 100 grams of ice from minus 30 degrees Celsius to the melting point, then melt it, then raise the temperature of the water to the boiling point, then boil it, then raise the temperature of that steam or water vapor to 115 degrees Celsius. So I'm color coding this because it helps me keep track of what I'm doing and where, and it also makes it look pretty. And that way we will do just one of these at a time. Here's our heating curve, looking on the y-axis at temperature. I also labeled these points that if we're using water for this, then the melting point or freezing point, same thing, is at 0 degrees Celsius. And the boiling point or condensation point, same thing, is at 100 degrees Celsius. As we increase heat energy, as long as we're within a state of matter, the temperature is going to increase. As we increase heat energy at a phase change, the temperature does not change because that energy is going into the process of doing the phase change, into changing that changing the arrangement of how those molecules are relative to each other, what makes them a liquid, and then changing how they're arranging to what they are like as a gas, like our wild, crazy kindergartners. So as long as we're within a state of matter, like as long as we're just heating water or heating steam or heating ice, we use Q equals M delta Tc. How much energy it takes is going to be equal to how much mass there is, times how much the temperature changes, times the specific heat of that water, or whatever the material is. How much energy it takes for the phase change is going to be Q equals the mass, how much there is, times that latent heat of fusion or heat of vaporization, depending whether we are at melting or at boiling. So how much energy does it take to melt or boil 1 gram times however many grams there are. I'm also going to keep like kind of a master list of givens here rather than relisting my givens every single time I do a part of this. So I think I'm actually going to start in the middle right here just because that's the type of problem we usually do. So right here where I'm heating liquid water, I'm going to do that part first. As far as my givens, I know my mass is 100 grams, and it's going to be 100 grams for the entire problem. My mass isn't changing. Starting with 100 grams all the way through. I also know the specific heat of my liquid water is 4.184 joules per gram degree Celsius. And my change in temp for this section, this part, goes all the way from as soon as it melted to the point it boils. So from 0 to 100, my change in temp is 100 degrees Celsius, and it's positive because it's being heated. So if I'm going to start with the middle here, heating water, I am going to have then Q equals M delta Tc because I'm within a state of matter. And there's my mass, my C, and my delta T. So if I have, where do I want to put this? Got to plan ahead. Mass is 100 grams times change in temp is 100 degrees Celsius times the specific heat of liquid water. Check my units. Grams is going to cancel. Degrees Celsius is going to cancel. 100 times 100 times 4.184 is going to be 41840 joules. So this right here is heating water. How much energy it took just for this section. Now we might as well go back to the beginning right here. Start with heating ice. So if we start with ice at negative 30 degrees Celsius is where we start. So this whole section right here is heating the solid water, heating that ice, which means if we're heating it within that state of matter, we're using Q equals M delta Tc. How much mass, how much is the temp changing, how much is the specific heat. So if I go back to add to my givens, it's still 100 grams. But this time my change in temp, I guess I could add to that, my change in temp of the liquid. This time the change in temp for the solid, the ice, is gonna be -30 to 0. So my change in temp for the ice is positive 30 degrees Celsius. And here's a new one. The specific heat capacity for solid water is different. The specific heat capacity for solid water is, for ice, is 2.1 joules per gram degrees Celsius. That it takes 2.1 joules to heat 1 gram of ice by 1 degree Celsius. So let's do that. Q equals the mass times the change in temp times the specific heat of solid water, of ice. And that is gonna be 6,300, and this is heating the ice. Okay, next part right here is melting that ice. So now I'm doing the phase change up here. Oh dear, could you see any of that? This part now, if I'm doing the phase change, I wanna know how much energy that takes. It's gonna be the heat of fusion times the mass. So heat of fusion, how much energy does it take to melt 1 gram times how many grams there are. So that's gonna be 100 grams times the heat of fusion, which I should add back over here to my given list. So the latent heat of fusion is 334 joules per gram. It takes 334 joules to melt 1 gram. And if I've got 100 grams, well, then it's gonna take 100 grams times 334 joules per gram. Those are gonna cancel. It's gonna give me 334 joules. And that's melting ice. Okay, so we've done all first 3 steps. Heating the ice, melting the ice, heating the water. Next, we are going to boil the water. If I boil the water, how much energy does it take to do a phase change? It's gonna be the latent heat of vaporization, how much energy it takes to boil 1 gram, times however many grams I have. So that means that we're gonna do the mass times however much energy it takes to boil 1 gram. So I'll add that onto my givens list. The latent heat of vaporization takes 2260 joules to boil 1 gram. But I have 100 grams. It's gonna be 226,000. 226,000 joules to boil our 100 grams. Okay, last step right up here. Now, once we've boiled that water, now we are heating the steam or the water vapor. So it says to raise the temperature of the steam to 115 degrees. So we're taking this up to 115 degrees Celsius, which means our givens, still 100 grams. Our change in temp now for the steam is 100 degrees up to 115. So our change in temp for the steam is gonna be a positive 15 degrees Celsius. Last given we need is the specific heat of water vapor, of gas water, because again, that's gonna be different than liquid water and different than solid water. So the specific heat of steam is about 1.9 joules per gram degrees Celsius. At this point, we're heating the steam within that gas state of matter. So we're not changing that. Or we're not changing the state of matter. We're not doing a phase change. So we're all within here. So I'm gonna move this, see if we can still see enough. So 100 grams, we're heating it to 15 degrees in steam times the specific heat of steam. Okay, that's the last part. How much energy it takes to heat the steam up to 115 degrees. Now, if we know how much energy it takes to do each individual one of these steps, how do we figure out how much energy it takes to do the whole thing? Well, how much it takes to do this, plus that, plus that, plus that, plus that. So if I list those, I'm gonna end up with add all those together. Plus 16, 7 plus 8, that's 15. And there are all 5 of those steps added together. So our final answer for the problem is 310,390 joules is how much energy it takes to take ice from minus 30, 100 grams of ice from minus 30, heat it up to melting, melt it, heat that water up to boiling, boil it, and then heat that steam up to 115 degrees.